Alrighty, guys, let's continue. So what we've done up to this point is we talked quite a bit about zero coupon bonds. So there are many other instruments now for fixed income, and we're going to go through a bunch of them, all the standard ones. So we're gonna walk through. And, so at this point, we have we have the money market account. We have the money market account, and we have zero coupon bonds for all maturities. M. So we can trade in the money market account, and we can trade in these zero coupon bonds with price process with B and M. So, so now we're going to look at fixed income derivatives. And arguably, the first one is going to be forwards. So the picture is that we are sitting here at time n, and there's some future date, say time capital N. Right. So at time n, you agree on a Kn, which is Fn measurable. So you're sitting here, you're agreeing on a constant, I shouldn't say constant here, you're agreeing on an Fn measurable random variable such that at time n, you get the asset and pay Kn. Like this asset here, there are two possibilities for this asset. So the first one is that it's a traded security. And the second one is that it's non-traded. A non-traded asset. So we just consider the first case. So case 1. So what happens is that, so say that Sn, this is the price process of the traded asset. All right, so the exchange is going to happen over here. The exchange is going to happen here, right? And there's going to be the value, if we're in case number one, let's denote by S here. This is something that you're going to get, right? So you get the asset, it has that value, and you pay K little n. So let's figure out what's the value of this thing is at time n. So this here is a convention. If the time n value of the payoff Sn minus k, so if the time n value of this payoff is 0, we call Kn for the forward price. So this is a bit confusing. This has been at least confusing in the past, that this Kn here, if it satisfies, then when I plug it in, so this here is the payoff we get at the end. If the time n value of this payoff is 0, then that K is going to be called the forward price, right? So this is called the forward price. Forward price. The forward price Kn, this is typically not 0, even though Kn makes the time n value equal to 0. So this can be quite confusing. It is, however, the name that stuck. This is what people call this particular Fn measurable random variable. So the value of a forward at a given point in time is equal to 0 when the strike is set to be that forward price. Okay, so let's compute. So the name of the game is to compute these forward prices. So to compute forward prices, we need to solve this is the payoff, right? So we roll it back. We're sitting out here. We need to roll this payoff back to time n. Okay, so how do we roll it back? Or discount it. Take the expectation. Discount it. Take the expectation. So Sn minus Kn. We roll it back to time n. So we divide here by Rn as 1 plus In plus 1 all the way up to Rn minus 1. And this here is the value. This is the value of getting, this is the time n value of getting Sn minus Kn at time n. So we want to solve, we want to find this coefficient here such that this becomes equal to 0. Okay, so what is Kn? Right, so we're working under the case that you have a traded asset. Right, so what it means is that Sn divided by Sn0, this is a P tilde martingale. Have to compute this thing. And of course, there are many ways to write this expression, where we could have written this as in terms of the zero coupon bonds. So I could have written this here as Sn0 divided by S capital N of Sn minus Kn. I could have written it like that. And we can also write this as, what would it be, E tilde, and we need a conditioning here, condition on Fn, condition on Fn. We keep the first part, Sn0 over S capital N0. Then minus, and then so we have Kn here. Remember Kn was we're looking for the forward price, so Kn has to be Fn measurable. And so we will be left here with Kn times the expectation of this ratio. So we recognize that this is the this expression here. This is my zero coupon bond. What I can do is I can write this the same. I can move the term over to the left-hand side. I have a 0 on the left-hand side. I'll move this over. I'll get Kn, and then the zero coupon bond. And capital N, this is the same as this conditional expectation we have here. Again, I'm missing the conditional expectation. So this would be E tilde Sn Sn0 given Fn, and I can put this money market account expression outside. And so if I know that this is traded, this is where I'm using that S is the price of a traded security. Then the conditional expectation of this ratio is just going to be the current value. This is going to be Sn times this Sn0. And we're ending up with Sn. So this is if the forward is written on an asset that is traded. And now we can solve. The forward becomes the forward price there's a unique solution to this, and it's Sn divided by the zero coupon bond. And just a sanity check, this is Fn measurable, and this is Fn measurable. This is Fn measurable. Questions on this? Any questions on the case of a forward price when the underlying is traded?
When should we write the F measurable condition?
Here? But that is actually the deal is that you're sitting here at time n, and you are agreeing on how much you're willing to pay for this this asset at a future time. So whatever you agree on at that time n, you can only use the information you have available at time little n. Like for example, if you're sitting here at time 0, right? N could be 0.
Oh.
So then this would be Sn minus a constant. If you're sitting here today and you want to write a forward contract, that's that amount that you're paying at a future date, that's going to be constant then. And there's only going to be one payment. If the payment is coming here at time capital N, there's only one payment. This is a one payment. Does it make sense?
Makes sense.
Yeah, other questions? Okay, so this was when the underlying was traded, but quite often. So the non-traded case. So an example here could be a forward on the interest rate. So you could have Rn. So here Rn is not a price process. It's a rate. And we don't have that Rn divided by Sn0 is a P tilde martingale, right? We don't have that. So what that means is that I kind of get stuck here, right? I cannot go from here to here because this is not true. So it begs the question, like, how am I supposed to compute the right-hand side? So we need a way to compute this right-hand side here. We need a way to compute this E tilde of whatever the underlying is. So like Sn divided by Sn0 times this Sn0 given Fn. So when Sn is not a price process. Because whatever I'm going to get here, this thing here is going to be equal to, like this is going to be equal to, it's going to be equal to my Kn, Bn, capital N. Right, and I want my forward price. So in order to get that, I need to be able to compute what this is. So this is a little bit problematic. And what we're going to do now, there's going to be quite a bit of notation here. And there are going to be some new concepts. So this is going to be, yeah, so hang on here now. This is it's going to be a little bit bumpy. So to overcome that, one introduces what's called forward measures. please note there's an S here, forward measures. These are denoted by P tilde, P tilde M. And there's a whole collection of them. There are lots of them. There's one measure for each time point. And so how are these guys defined? Well, the way that it goes, you define through their Radon-Nikodym derivatives. So maybe we should recall that. So just to recall, if I have two meshes and I look at their Radon-Nikodym derivative dq dp, recall that this one is a Radon-Nikodym derivative. If what? Well, we need a bunch of properties. The first one is that it's, I think this goes from omega to the positives. It's a random variable. I need the expectation of it to be 1. Right? This expectation is computed under P. I'll put a P up there if you want. And then the property is that it links these two meshes. Q on a set A can be computed by integrating over A of this Radon-Nikodym derivative with respect to P. Or if you want, you can write this as an expectation, again under P, you can put a P here if you want, 1A dq dp. So these forward meshes that we're now going to introduce, they are going to be described in terms of their Radon-Nikodym derivative. And it's going to be their Radon-Nikodym derivative with respect to this measure P tilde up here. So the way that it's going to go is that we're going to define dp tilde m dp tilde. This is the Radon-Nikodym derivative. The forward measures Radon-Nikodym derivative with respect to the martingale measure P tilde. Okay, so there's no P here. And so the definition is you need 1 divided by the money market account. And you note this M here is the same as this M here. So this is going to be positive because it's the money market account. So we go on that, but we also need this expectation to be 1. I also need this expectation to be 1. So the way that I do that is by dividing everything by its expectation. So no doubt that this thing here is positive. There's also no doubt that if I take the expectation, under the tilde measure of dp tilde m dp, this is going to be 1. Right? Because it's the expectation of this ratio. This is a constant. You can travel outside the expectation, and I'm left with the expectation of this guy, but that's exactly the same thing as 1 divided by. So this is a good random variable to use for the Radon-Nikodym derivative. Are there any questions before we launch into calculations? Like this quantity we have down here, for example. This is my zero coupon bond. Are there any questions? Another thing to note is, for example, if R, the interest rate, if this ended up being, if this interest rate process is non-random, so this is another word for that is deterministic, well then the expectation of 1 divided by S is M0, because it's non-random, that expectation will just be itself.
Hello, you forgot the F measurable.
Can you say that again?
F measurable.
For which one?
E tilde.
E tilde. Where do you want to put the F?
The last line.
Here? I want to compute what's inside this red box here. And so if this is not random, like what we had in the case of the constant interest rate, then the zero coupon bonds would just, you would be given as 1 over the money market account. And there will be no randomness here, so the expectation is, of course, the same thing as without the expectation.
Okay.
Then you see the ratio now. This is the same as what you have up here. And this is going to imply that dp tilde over dp tilde m over dp, this is equal to 1. In other words, so forward measures are only relevant when Rn is stochastic. If you have deterministic interest rates, there's no need to worry about forward measures because they're always the same as the risk neutral one. This is why we haven't seen forward measures before now. Okay, so why is it good to have these forward measures? Well, let's try to do a calculation. We're gonna need the radon Nikodym derivative process. The radon Nikodym derivative process. So what is that? It's going to be this E tilde N over dp tilde M dp. And this is what we call ZMN. I can put a parentheses up there. So what do we get? This is defined for n being 0, 1, all the way up to m. And so something to note is that, well, one of them is, if I look at it at the first one, now this is just going to become the expectation. And that's the one we started out with. That's going to be equal to 1. Another thing we should note is that C and M, this is going to be positive. And we should also note that Z and M, when I index it by time, this is, again, this is a Levy martingale. Because I think we had it earlier today at some point. Let me just find that slide. This is right here. If I take a random variable that does not depend upon n, take a random variable a that doesn't depend upon n, I condition, I get a martingale. So a is a random variable, doesn't depend upon n, condition, I get a martingale. It's exactly what I have here. Take a random variable, I condition. This random variable doesn't depend upon n, I condition, I'm going to get a martingale. Let's try to work out what we have here. Can we work out what this thing is? So C N M tilde, this is the expectation under the tilde measure of this dp tilde m over dp. So it's this mess that I have here. It's this mess I have here. So it's 1 over SM0 divided by the zero coupon bond. Okay, let me copy paste that in there. So it is 1 divided by SM0 divided by the zero coupon bond. Okay. It doesn't make it any better. Well, a little bit, because well, I can pull out, this is a constant, right? He's F0 measurable. This quantity can go outside. So I'll have 1 over B0M. And then what I have inside, I'll have SM0 downstairs. And so now what I want to do is I want to multiply upstairs with SN0, which is Fn measurable. Right, so I can divide out here by SN0. I didn't change anything. This quantity here can travel inside the expectation and cancel this one out. And now what I have here, this quantity, this is my zero coupon bond. So what I'm seeing is I take the zero coupon bond and I discount by the money market account. I know this is a martingale, and then I divide by some constant. But this quantity here, this is exactly a P tilde martingale. Because it's the value of a traded security, it's the price process of a traded security divided by divided by the money market account. This is going to give me a p tilde martingale. It was this property here that we started out looking for at the very, very beginning, all the way over on slide 4 in the beginning of today's lecture. We took the zero coupon bond divided by the money market account. We wanted to get a p tilde martingale. And here it pops up again. So my Radon-Nikodym derivative process is given as the discounted zero coupon bond prices and then times some constant. And this one here is just a constant. So why is the Radon-Nikodym derivative handy? Well, it's handy because well, one place it's handy is if you combine this Radon-Nikodym derivative process with base rule, you get the following. So base rule, which we had talked about before, it says that Mn is a p tilde, say m martingale, if and only if something is a p tilde martingale. Does anybody remember what it is we have to do to m to get the martingale property on the p tilde? We need to do something to m in order to get that. So if I have a p tilde m martingale, it's not necessarily p tilde martingale. We need to do something to it. Yeah, Don, that's the definition of being a martingale, but right, what I have, so if you are to go downstairs, right, so we would have to have E, what I know is E tilde M, Mn plus 1 given Fn. If I am under this, maybe I should write it all the way out. The expectation on the P tilde M, I say I have the martingale property. So if I go down, if I'm looking at proving it downstairs, will I also have then that E P tilde of Mn plus 1 given Fn? Would that also then be Mn? Or should I do something else here? Anybody remember what we need to do to M to get the martingale property? Maybe we should recall base rule down here. I am to compute an expectation on the P tilde M of say a random variable A given Fn. Like what base says is going to multiply onto the Radon-Nikodym derivative inside here. So this will be d P tilde M dp times A given Fn. Then you have to divide by the conditional expectation of the Radon-Nikodym derivative given Fn. So this was a base rule. This was something that was in, it's been a while since we did that. We did that before your midterm. It's a base rule. What it says is that if I take a martingale under the p tilde measure, I need to take the Random derivative process in here. Then this is a martingale, right? So let us assume this, and I'm going to try to prove this. Needs to be shown, but it's not too bad. If I use base rule down here, I'll get the assumption is the top part, and I want to show this part. So how would I go about doing it? I'll use base rule to work on the left-hand side. So I'll work out what the left-hand side is. This thing here is equal to all this mess we have down here. So this will be E P tilde, and then the random derivative C M plus 1 C n plus 1 m n plus 1 given Fn divided by the random derivative. This was Cn. Right, so the left-hand side is equal to this, and then I can just move this term here on the other side, and I get this part. So base rule says that if I know what the random derivative process is, I can also figure out what martingales look like under these meshes. Okay, so what we have now is if xn is a wealth process, right, so this is a traded security, then I know that xn divided by Sn0, this is a P tilde martingale. We had that one earlier today too. And so what's the claim? Well, the claim is that xn divided by bnm, this is a P tilde m martingale. That's a proof of claim. It's exactly that scenario that I have up here. I know something is a martingale. I know something is a martingale on the P tilde, but I don't want to get a martingale property on the P tilde m. So if I'm claiming that this is a P tilde m martingale, well then, what's the proof? Well, I'll use that result up there. This is a P tilde m martingale if and only if. What do I need to do? I need to multiply onto the random derivative process. So this will be xn divided by b n m times c n m. This is a P tilde martingale. And now what we can do is we can go back and use the formula for my z process. go back and use the formula for my C process, plug that in here. So I have xn divided by b and m. And I'll plug in what this expression here is. This was b and m over Sn0 times 1 over b0 m. This is the same thing as saying that this is a p tilde martingale. And now it cancels. And I'm left with xn over Sn0, constant. And we already know that that's a p tilde martingale. So you see what is happening with these measures is that for the risk neutral measure, you need to discount by the bank. So this is discount by the bank. To get martingales. If you want to look at the forward measures, well, here you need to discount by something else. You discount by the zero coupon bonds to get martingales. So now we go back and now we're going to use all this material to resolve that question that that we had in the very beginning. This was quite a bit of a detour, and the 5 slides earlier, we were looking at forwards, and we were looking at forwards written on an asset that was not traded. So what does that have to do? What does it have to do with? I mean, what does it have to do with forward measures? Well, we have this. This is our requirement. Right? So what we have in here, I want to use the forward measure to say something about it. So back to these forwards. Let me get some more paper. So back to forwards. Where it is Sn is not traded. We still have this formula. We're trying to work out what it is. So we still have this formula here. Still have this formula here, so we're still quite interested in. So I'll just copy paste formula. So this will be 1 over b n n times this expectation. Let me put the money market account back inside here. So I'll have Sn0 times, and then the value of the non-traded security. So how do I get this thing to work? I want to use, so no, we want to express this. So we wish to express Kn in terms of p tilde, it's going to be p tilde n. And how would we go about doing that? Well, if I'm looking at an expectation under P tilde n of say Sn, how would base demand that we do this? So this is again base. Base would say that what has to happen is you have to compute under the tilde measure, multiply the radical derivative in there. So this is Cmn times Sn. And there's a condition missing. So there's a condition. And then you have to divide by Cnn. So this looks like a mess. Let's try to work out what the mess is. Well, I think I messed up my n's and my m's here. This is an n here, so this one here should be an n. I need to go back and find my radical derivative process. That was this guy here. And so one thing to note is that when n and m are the same, I'm going to get a 1 here. Okay, so let me plug in the two quantities. Let me start with what's downstairs. So I'm just going to copy paste everything I have here. This will be B, N, and again, this should be a capital N. Divided by S and 0 times the 0 coupon bond. Okay, so this was what I had downstairs. And now I need to write the same thing as what I have upstairs. E tilde. And now this mess here is going to go in there. So I need to have n and m both be capital N. So that's a 1. I get 1 over Sn0 times 1 over B0n times Sn given Fn. So what will I get here? These two things will cancel out. This will cancel with this one. This one here, he can travel inside. He's measurable with respect to Fn, so I get 1 over Bn n conditional expectation is Sn0 is capital N0 times Sn given Fn. So here's the magic part. When I'm comparing this formula here with this formula out here, it's the same thing. This here is exactly my Kn. And this is why it's called a forward measure, simply because the forward price, the strike price, is given as an expectation of the terminal value of this payout of this asset that we're exchanging, but you have to compute it under those under the corresponding forward measure. So this formula here is this is a thing that will be used over and over when it comes to forwards, written on an underlying that is not traded. Okay, are there any questions or comments on the forward price when the underlying is not traded. So the next derivative that we're going to be looking at is the futures contract. And very often futures and forwards, futures and forwards, they are highly related. But just keep in mind, at least at this point, that if you were to compute forward prices, you're going to need the forward measures. Right? So you're going to use forward measures to compute forward prices. And the thing to note is that this is different from futures. So the forward measure goes together with forward prices. The futures, on the other hand, this is different. Okay, so now we're going to be talking about futures. I should also, before I forget, I should say that the textbook notation, if I can find it. The textbook notation for this K here, so this is our textbook. You will call this for 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 the forward price. Then you would have like an N and then a capital N. This is how he writes it. FOR N capital N. This is what he writes for K. So futures are different. Futures, there are now multiple payments. I recall with the forward, there was only one. I recall here with the recall here with the forward, there was just one payment, right? There was this one block where there would be a payment. So now with the futures contract, this is different, and there's a standing joke that the difference between futures and forwards is trust. Right. So here you kind of trust that the guy that is supposed to pay you, he doesn't default, disappear in the period between now and when you're expected to get this payment. Just imagine that this difference here, as you move along, this difference here could widen up. So you could look at it with the forward. With the forward, right? You're interested in this difference. You're interested in this difference, and then it becomes Sn plus 1 minus Kn. Then it's going to become Sn plus 2 minus Kn, and so on, and then all the way up to Sn minus Kn. Right. So say that Sn plus 2 minus Kn is big, and for example that Sn plus 3 minus Kn is even bigger, right? So and so on. This means that you're expecting a large payment at time n, right? The payment you're going to get at time n is going to be Sn minus Kn. But as you can see, this over time, it widens up. But of course, you're afraid, you are concerned, you're afraid that that you might not get it. Could be the other part defaults or runs away. Right, so when you see this thing widening up, you are worried now that this is happening gradually over time, and if you're looking at the difference here being maybe you're striking a deal that will be like a month in the future, and you see that this thing widens up, which means that you're expecting a very large payment. At some point, you're going to start to worry about whether or not this is actually going to happen, because it's so much money, and the counterpart that's supposed to give you all this money, well, you don't think he really has it, and so what that means is that you're not going to get what you're owed. I just think about it. If you take out a loan and you owe your bank or your mortgage company $1 million. Right, there's a big difference between you owing them $1 million and then say that $1 million grow to $1 billion. At some point, it goes from you having a problem to the bank having a problem, right? Because if you suddenly start owing them too much, then they're going to become afraid that you can't pay it back. And the same line of story is going on here, that if you see what happens with the contract over time, the gap widens, suddenly you really like it to be positive, right? Because if this thing is positive, you're going to get money at the end. But if it widens out to become humongous, well, then it's unlikely that you're going to get your money, right? Because the other part is going to default or run away, or yeah, he's not going to pay you what was promised. So the futures, these seek to deal with this. There are going to be multiple payment dates. So let me try to write out how the mechanics work for a futures contract. So there's going to be payment. There are going to be payments over n to capital N. Right, so they're going to be sitting here time n, and the game ends over here, and they're going to be payments here, and they're going to be payment here, and so on. They're going to be payments over there, and the payments, this happens according to a futures price process. And this price process, this is going to be denoted by, I'll denote it by phi. We're going to have these payment dates. We're going to start out here at n, and we're going to run all the way up to capital N. So we're going to create this process. And how are we going to create it? Well, we're going to start. It's going to be pinned down at the end, phi, and this is simply just going to be Sn. Right. So in the last period, when you're out here, you're just going to have the underlying. So at the end, it's just going to end up being the underlying, right? This, we call that Sn is the value of the asset at time n. Now see out here at the end, this futures price process is pinned down to be that. But of course, at earlier times, so now we're going to construct phi n plus 1 all the way up to phi capital N minus 1. We're going to construct is as follows. And how are we going to do it? Well, we start out with the first one. At time n, what we're going to do is we're going to invest phi n in the bank. And so that's one thing we're going to do. And the other thing we're going to do at time n is we're going to buy, putting this in quotation, we're going to buy, so that is colon, 1 plus R in futures. But you don't cost anything to enter. Futures, just like for the forward struck, at the forward price, futures are free to enter. So we enter, we go long, a number of futures, this 1 plus Rn, right? This is a random number, but of course at time n, I know what Rn is. So then what unfolds is that at time n plus 1, what happens? Well, we put this amount in the bank, right? So that has grown. We have my phi n in the bank, and then it's grown with 1 plus Rn. So now they're going to be these futures payments. So now they're going to be futures payments. Futures payments. On the next slide, so they're going to be futures payments, and this is what's called marking to market. Marking to market. So they're going to be futures payments because we are in a futures position that is not 0. So we're going to receive, that's because we're long. What are we going to receive? Well, the thing we're going to receive, it depends upon how many we have. We had 1 plus Rn. This was 1 plus Rn. This was our futures position. This was our long futures position. And then depending on the futures price process, that's the phi's that we're ultimately trying to determine. Depending on what that thing is, we're going to get this payment. So we're going to receive this. We're going to receive this amount. Depends upon the futures price process times the position that we have. And this is going to get deposited. And we deposit into the bank. This is going to give us a net bank now. We're going to add these two things together. This is what we had from the previous period plus the interest rate plus this thing. And now you can see the cool thing is that it cancels out a little bit because there's a minus phi in here and there's a plus phi here. So you'll cancel out. So the net bank position is 1 plus Rn times phi n plus 1. So what else do we do at time n plus 1? We're going to buy more futures. So overall, futures position, that becomes, it will be this 1 plus Rn, like we had 1 plus Rn here, and now we're going to have 1 plus Rn plus 1. And so again, this is free. There's no cost associated with entering this futures position. So we just keep going like this. So at time n plus 2, what happens? Well, this is what we have in the bank. This is what we have in the bank, right? So we're going to get interest. We're going to get interest on this. So it will be phi n plus 1 times 1 plus Rn. And now we're going to have interest going from time n plus 1 to time n plus 2. That interest is 1 plus Rn plus 1. Then we're going to get futures payments. What are the futures payments? Well, it depends upon our futures position. This is our futures position. 1 plus Rn, 1 plus Rn plus 1. Just as before, take the position times the change in the futures price. So this will be phi n plus 2 minus phi n plus 1. And this is going to get inserted into bank. So then the net bank is going to be the sum of these two. Add these two together. And again, as before, they cancel out. I get 1 plus Rn, 1 plus Rn plus 1 times phi n plus 2. So now we recognize the pattern, right? We just keep going like this. And then we want to enter more. We want to enter more futures contracts. So it becomes this thing times 1 plus Rn plus 2 and so on. And you keep going. And at the end, at time n, what is the net thing you're going to have in the bank? Well, the net thing you'll have in the bank is going to be exactly this 1 plus Rn times 1 plus Rn plus 1 times 1 plus Rn plus 2, all the way up to 1 plus Rn minus 1 times phi n. Right, so n plus 2 here, this now becomes n. And here you have, well, the one before, this is R capital N minus 1. And now we use the condition that at the end is going to be exactly Sn. So this is equal to 1 plus Rn, 1 plus Rn plus 1, 1 plus R capital N minus 1, and then there's going to be Sn here. So this is the value in the bank. And so the price at n for this payoff. So this is this payoff, I should say for the payoff, 1 plus Rn, 1 plus Rn plus 1, 1 plus Rn minus 1 times Sn. The price here, this is given by a discount. So a discount, this is E tilde conditional on n. I will discount it back to time n times this 1 plus Rn, 1 plus Rn plus 1, 1 plus Rn minus 1 times Sn. But I know also what this must be. But this thing here has to be, whatever it cost me to get this game started. And the thing that it cost me to get it started was exactly phi n, right? Because I put phi n into the bank, and this here didn't cost anything. So the price of getting this game started was exactly phi n. This was exactly phi n, and then we can use the money market account, what this here is, and you can see that this ratio is exactly what I have here. So the left-hand side, this is E tilde n of Sn. So that's what this is what the futures price is. So to summarize, if I'm looking at forwards, the forward price, Kn, this is equal to the expectation under the forward measures of the terminal value of Sn. In the futures, this is given as phi n is equal to E tilde n, but there are no forward measures. This is just a risk neutral one. Right, and they're the same. Do you agree? We agree if P tilde n is equal to P tilde, i.e. if Rn is non-random. So we have a futures price and a forward price process. They're given by these two formulas. One, for the forward, you compute conditional expectations under the forward measures. For the futures, you compute conditional expectations under the risk neutral measure. And I should also say here that our textbook likes to write, so this is our textbook. Our textbook writes FUT n n. So no, we did a lot of writing today, but I think this here is a good place to see if there should be any last questions. If not, then I think this is plenty for today. We did futures and forwards here in the second part, and then we did zero coupon bonds in the first part. Next time, we'll do some examples on how to compute these and how to compare them when the interest rate is stochastic, of course, because if it's a deterministic interest rate, there's no difference. Are there any questions or comments before we end? Are there any questions or comments? So let me just end with the same slide as the one we had in the beginning. Have a look at the updated syllabus. Contact me for a time slot regarding the final exam. And please note that there are some changes to the schedule in the week around Thanksgiving. In particular, there's no homework due. There will be a TA session tomorrow. And then there'll be office hours on Thursday and Friday this week. The homework this week is a little bit different. Put up a set of homework problems related to basic probability questions. So some of the things that I saw come up during the midterm oral exams, this homework here tries to help out a little bit on addressing some of these issues. Are there any questions before we say goodbye? Alrighty, I will see you guys hopefully Thursday and Friday morning, and if not, I'll see you guys on Tuesday. Have a good day, guys.